Hi, I am Brad Huang, an undergraduate student at the University of Waterloo. I'll be talking about an algorithm to size solar panels and storage for multiple
That sounds okay, right?
Yes, yes, yeah.
Okay, okay, great.
roofs. I've completed the work under the kind supervision of Fiodar Kazhamiaka and Professor Srinivasan Keshav. Nowadays, solar and storage systems have been increasingly adopted, not only as an environmentally conscious choice, but also a financially savvy option in the long term. However, it is still an expensive upfront investment, costing an average American family $19,000 to $57,000, depending on their energy needs. So, to increase the adoption of solar energy, it is still very much necessary for us to present more affordable systems and optimize for cost. The big question we're interested in is what is the cheapest combination of solar PVs and battery sizes that will meet electricity load needs? And it is essentially a balancing act of robustness, where quality of service should not be violated due to small, routine variations in either weather conditions or load, as well as the affordability of the system. Now, we have studied this question to some extent with presentation at past conferences. In 2018, we compared several approaches to the robust sizing problem and then refined it in a journal article. In 2019, we looked at how to get around the problem of consumers who do not have access to load and solar measurements. And this year, we're looking at a complex but fundamental problem, which is sizing for multiple roofs. We came across the problem when folks at a British Antarctic survey approached us to consult on a decarbonization project at the Rothwell Research Station in Antarctica, sizing solar panels and battery storage on 5 available buildings, each with a different solar profile and limit on how many panels a roof can hold. And that's when we realized the problem is much more complex than the single roof version. So intuitively, the reason is that some roof segments may have a higher load potential for solar energy production because they're facing the right direction, but they also have a higher installation cost or smaller panel capacity, or vice versa. Now, there are existing solutions available in the industry to tackle the sizing problem as well. 2 examples are Tesla's simple preliminary calculator, which gives enough of a rough estimates based on your location and monthly electric bill, as well as NREL's Reopt calculator, which is more specific, asking for more data, and performs some kind of optimization for either cost or robustness. But most solutions, including our previous solution, make a simplifying assumption that all panels are installed on a single roof with the same incline and orientation, and the roof can hold a limited number of panels. So our contribution this time around is that we formally state the multi-roof sizing problem, present and implement an algorithm for it, and evaluate the algorithm by validating empirically its robustness and effectiveness on multiple years of residential data, and calculating a hypothetical multi-roof sizing of the Rothwell Research Station in Antarctica. To formulate the problem, there are a couple of parameters for us to consider. The first one is the hourly traces, both the solar profile, which is the generation potential for each unit of PV on each roof, which could be different, and that's dictated by the orientation of incline of a roof and the weather conditions, as well as the load profile dictated by human behavior, which are a lot less predictable. For example, this is a day of residential solar and load profiles shown on the figures. The second factor we want to consider is cost. Solar installers can often charge a fixed cost for accessing a roof segment, as well as a marginal cost per unit of PV. For example, accessing one roof could cost you $2,000, no matter how many panels you put on there. But accessing another roof could cost $5,000 because the latter roof could be higher or steeper and it's hard to access. On top of that, it could be, for example, $2,500 to install 1 kilowatt of panels. For batteries, we only consider marginal costs. Lastly, there can be a capacity limit on how many units of PV we can install on the roof, or how much battery we can have in general. And that could be because of size or weight or room constraints. We then look at the cheapest sizing that satisfy a quality of service requirement, which is expressed using three other parameters: the confidence interval, the sample period, and the loss target on which we calculate, which is either the expected emet load over the period, or EUE, or the loss of load probability, or LOLP. As an example in English, we could say that we're 95% confident that over any 100-day sample period, the system can provide over 90% of load in total in that period. That will mean a 10% of unmet load. Or if we use LOLP, we could say that the system can satisfy the load 90% of the time during that period. And again, our goal is to find the cheapest system within the limits that satisfies the quality of service constraints. Now, before diving into our multi-roof algorithm, I will offer a brief overview of the single-roof algorithm. First, we'll subsample the hourly PV and load traces. We'll then compute a set of most efficient PV and battery sizings called the Pareto frontier for each subsample. Finally, we'll compute a Chebyshev bound to ensure robustness and present minimal cost result on that bound. So we'll break that down later. Now we'll take a bit of a deeper look. So we'll first take a number of subsamples to the PV trace and the corresponding load trace at the same time, each of length equal to the sample period t, as you can see on the graph. The number of subsamples depends on the confidence interval and the Chebyshev parameters. Usually around 100 subsamples should be enough. This process is the same for both single and multi-roof algorithms, except each roof or multi-roof algorithm would have its own PV trace. Now, in the single roof sizing algorithm in each subsample trace, the idea is that we'll start with the maximal amount of PVs. We'll then use the battery charging and discharging simulation to determine the minimum battery needed to satisfy the quality of service we mentioned earlier. We'll then decrease the PV allocation by 1 unit and rinse and repeat, finding the minimum battery for that amount of PVs until we'll repeat the process until we can no longer satisfy the quality of service even with the maximal amount of battery. And by doing that, we essentially find a Pareto frontier where the PV and the battery trade off with one another, and on the curve, it is impossible to decrease any allocation and still achieve the same quality of service on that subsample. As we can see on the graph here, that will be an example Pareto frontier for one subsample. Now we'll repeat the process for all subsamples. And here, each Pareto frontier corresponds to one subsample. Now, this ideas work fine when there's only one PV and one battery to consider. So we're essentially conducting a linear search on a one-dimensional search space, which is the PV. But unfortunately, it becomes intractable for multiple dimensions, even 2 dimensions, because the linear search will become a grid search on the surface, causing a combinatorial explosion. So I'll explain what I'm talking about in here. This is a grid search example for one subsample with 2 rooftops. The X and Y axis each represent a PV allocation on each roof. For each pair of PV allocation, we still calculate the minimum amount of battery needed to satisfy the quality of service. So that will correspond to each coordinate in the figure here. And then we will calculate the total cost of the system, which is indicated by the color here. Essentially, each curve we see before, now it becomes the surface. So we should no longer calculate this kind of exhaustive search on the surface if we want a result in a reasonable time. Instead, we're interested in directly finding the minimal cost sizing in each subsample as marked as X here. So that's what we're trying to find. Note that this is a smooth surface, so we can use stochastic gradient descent or some other form of optimization algorithm to find the minimal cost sizing that satisfy the quality of surface in each given trace. We'll start from the maximum allocation here for all PVs and use cost as the objective function that we differentiate on. Now this is an example run, going left and to the right, finding the X. In our implementation, we're using add delta, which has worked well for different cases without us having to tune any parameters. Now this is the whole surface for one subsample, and each one of them will have a minimal sizing for us to calculate. going back. Okay. After the minimal sizing for each subsample is calculated, we'll then calculate the final result. So in the figure, each of the blue/red dots represents one of the minimum cost sizing coming from one subsample. So the idea is that if we were to use analogy with an egg, are that the sizings are calculated with known data and are like the egg yolk. But because of our result sizing, we need to deal with unknown data in the future, which likely have some kind of routine variation. We want to be robust and leave a buffer like the egg whites and offer a sizing on the egg shell, that is the minimum cost. So now what we need is to find the location of this shell. And this is done by multivariate Chebyshev bound, where each individual sizing is treated as samples from a set of independent, identically distributed random variables, which stems from the variation of PV and load. Finally, we will find the minimum cost sizing on the Chebyshev bound, as shown as the yellow here, which is the egg shell, as marked by X on this example as the final result. So to summarize, the multi-roof sizing algorithm would sample a number of corresponding PVs and load traces as before, and for each load, PV and load trace, search for the minimal cost PV and battery sizing that satisfies the quality of service requirements, rather than exhaustively search all combinations of PV allocation, and use the multivariate Chebyshev bound to provide robustness of the result. Now we look at some of the evaluations of the algorithm. We've validated the algorithm on 49 residential homes in Austin, thanks to data from Pekin Street. Each house has its own 4 years of load data with its different usage patterns. For solar patterns, we'll pick solar profiles from 2 of the houses facing different directions and use them as the PV generation profiles for 2 roof segments for each house. We've performed leave 1 year out validation, basically computing the sizing of 3 years of training data and validating its unmet load over the remaining year. This gives us 4 experiments for each house and 296 total experiments for us to validate on. The result is promising. For a confidence level of 85%, only 4.1% of the sizings that have been shown to violate the quality of service requirements, with a met load greater than the target, which is 10%. These would be the bars to the right of the red vertical line. For 95% confidence, the sizing will be more expensive and conservative, but we only see 1% of the sizing having loss greater than 10%. Now, the ideal situation is that with 85% confidence level, we'll have exactly 15% of the sizings going over, and with 95%, 5% of sizing going over. And that would have made the sizings cheaper, so our results very closely err on the conservative side. But that also confirms that our algorithms produce feasible sizings that are robust to variations in the solar and load profiles. We've also compared our algorithm with Tesla's preliminary design calculator for the same set of data. Note that this is not an apple-to-apple comparison and is for reference only. Tesla's calculator likely have different objectives in mind, one of which is convenience for the users. Because the only data that Tesla takes are the location, which for us is Austin, and an estimate average monthly bill, which for us amount to $165 for all houses, since our data is normalized. Therefore, for all houses, Tesla suggested a 12 kilowatt system and 3 Powerwalls, which is 40.5 kilowatt hours of battery. We'll plot the results by the validated loss on the x-axis and the cost of the system on y-axis. So this is the one size for all sizing suggested by Tesla. You can see that most systems have very low loss value, less than 0.5%, which is great. But a few outliers have a very high loss, more than 10%, which is not great. In our experiments, we will target for a 5% loss, and that would look like this. So the results from sizing suggested by our algorithm are colored by orange and connected by a line to the corresponding Tesla sizings with the same house. And because our algorithm relied on more data, it was able to generate a more custom sizing based on each house's needs. So each sizing for each houses have different costs and different losses. Therefore, they have a more consistent loss metric. In fact, no house has exceeded our target loss, which is great. The average cost for our sizings are 6.5 lower than that of Tesla's, although there are a few outliers on cost. Now, I like to highlight from some specific cases. First of all, there are opportunities to bring down the cost for the houses with very low loss. In fact, half of these houses with 0.5% losses with the 12 kilowatt system still has a less than 0.5 houses with an 8 kilowatt system, which is a third smaller, both in PVs and in battery, than Tesla has suggested. With our algorithm, we're able to give them an average of 8.4% saving. Occasionally, our algorithm suggests a more expensive sizing than the Tesla's algorithm. In these cases, we found often a large variance in load profiles across years, which results in a more conservative but robust sizing. And finally, our algorithm found a generally better sizing for houses that have abnormally high loss with Tesla sizing, the outliers with more than 5% loss, as you can see here. For these houses, our algorithms find a smaller sizing than the cheaper system while meeting the quality of service target better, reducing the loss. For these types, our sizings generally have a larger allocation of battery and less solar panels. The difference demonstrates the effectiveness of the algorithm and shows the benefits of considering load profiles rather than only monthly bills. Finally, we are able to apply our algorithm to a case study of decarbonizing the Rothwell research station in Antarctica based on real measured data. So far, the station has been powered with diesel generator that use on average 16 cubic meters of fuel per month, which is carbon intensive and requires even more fuel to deliver to such a remote location like Antarctica. We're hoping to offset 35 to 55% of such needs. Because of the station is located in Antarctica, the solar pattern is different from what you would see in other locations, in that in its summer month in Antarctica, you got sunlight almost 20 hours a day, whereas in its winter month, you got almost zero sunlight, which makes it very easy to fulfill a small portion of the load in the summer, but much harder as the portion of load as we want to replace increases, as we'll see later. Another interesting point of this case study is that two of the buildings are north-facing, which in the southern hemisphere receive more sunlight than the others, as you can see here. However, note that the Bonner buildings on the left have a very small roof capacity, and the exact opposite is true for the hangar building, which receives less sunlight but a very high capacity. So there is basically a trade-off between radiation and roof capacity, and it'll be interesting to see what choice that the algorithm makes. So here are the results when we want to replace 35% of the total load. Note that only two roofs that receive the most sunlight, Admirals and Bonner, are needed to satisfy the load needs, and any battery is barely needed with only 3.8 kilowatt hours of battery. Compare that to when we want to replace 45% of the load. We'll need PV installed on 3 roofs, significantly more PVs, and significantly more battery as well. The cost of replacing 10% more load is almost tripled. Lastly, when we want to replace 55% of the target load, we need 4 times more battery to sustain the nighttime load, likely during the spring and the fall, and the cost doubled to compared to 45%. A non-obvious choice was made by our algorithm to not include Bonner, but the larger hangar roof, because of likely both the fixed cost that will incur by installing on 3 roofs rather than 2, and that a combination of two roofs can spread out the PV generation over the course of a full day, essentially complementing one another. We tried the algorithm to replace even more load, but it became entirely infeasible. But with this result, implementers can make an informed decision that balances the economic and environmental impact. This further shows that our algorithm is valuable in making practical and robust choices. That being said, our work is not finished here. There are computation and statistical improvements that can be made. Try faster and less memory-intensive optimization and bound-finding algorithm compared to our current ones, and eliminating some unintuitive results because of some different sizing preferences across subsamples. And lastly, we hope to extend the algorithm to optimize for net metering, where it is an option to sell excess energy back to the grid. We hope you liked our presentation, and if you like to try the algorithm out, it is open source on GitHub, as well as hosted on a website as a calculator. The single roof algorithm is live, and we're working on integrating the multi-roof algorithm, and we appreciate any feedback. In summary, the multi-roof sizing problem is a common and more complex setting that makes the solution more practical and allows stakeholders to make more informed decisions. And it was not widely considered in prior works. We've extended our previous approach to sizing by developing an algorithm for the multi-roof sizing problem. The novelty comes from a more efficient way to search the space of the Pareto-efficient sizings and using the multivariate Chebyshev bound to ensure robustness. We've shown the algorithm is robust and efficient and works well with real-life cases. And finally, we'd like you to try it out and appreciate any comments and suggestions. And with that, thank you for listening.
Thank you to Brad and to authors of this paper. Professor Keshav is here. So are there any questions from the audience? So, Keshav, I had a small question. I don't know if it is obvious or typically in the sizing problems, not only in your work but also work of other authors in this session, we kind of assume that there is a size that is available and work on optimization according to those sizes and the historical data and so on. But one of the challenges that occurs in practice is that when the person who comes to install the panels and the battery, etc., right? The battery that is installed may not actually match the values that we had input in the optimization. The solar panel that is installed may not actually exactly match the values we had used in the optimization. So is it obvious to incorporate some kind of a tolerance error in the optimization to handle this problem, or is it it's like a different problem altogether?
No, indeed, what you're saying is precisely correct. Not only is it the solar and storage are slightly different, it's also the case that the future is slightly different from the past. And that's why the focus in our group's work has been on robust optimization, where we use a Chebyshev bound and we advocate sizing slightly differently. So on a more philosophical note, any optimization problem is going to give you a brittle solution, right? Because because optimization is tuned precisely to minimize the objective function on the input data. So if the input data changes because the future is unknown, or as you pointed out, the parameters of the system are slightly different, what will happen is that you're going to get a system which is perhaps very far from optimal because it's not robust. So what we do is we compute a set of sizings rather than a single sizing, and then we compute a Chebyshev bound on it on the kind of principle that the set of sizings constitute unknown distribution, and each of them represents an IID sample of the unknown distribution. And so then we can use a multivariate Chebyshev bound, and this robustness in the bound is basically what allows us to deal with the unknown future, and the same robustness should also allow you to be robust to minor variations in the parameters of the storage system or the solar. In contrast, if you take the don't take the Chebyshev bound, then you're going to be having a solution which may not meet the QoS requirements if there's any variation.
Okay, yeah, thanks, Keshav. Any other questions from
question
anyone?
from Mohammed, it says any information about the computational times and complexity. So Mohammed, the computation time and complexity for the single roof was in the paper from 2019 eEnergy, and I don't remember the exact formula, but basically optimization in general is n to the 4, n to the 5, something like that. And so it's very, very slow. And what we are using is essentially simulations rather than optimization, because we found that simulation is and stochastic network optimization, stochastic network calculus approaches both have similar time complexity, which is substantially less than classical optimization. So here we're using simulations. The simulations are basically the number of time steps, and in each time step, the operations are very, very simple. It's just addition and a subtraction. So it's very straightforward. And so the overall computation cost is dominated by the number of steps taken in the stochastic gradient descent. And of course, SGD it's not a bounded optimization problem. You know, it can take very large number of steps depending on the nature of the surface. Now, in practice, we found that the surfaces we're looking at least in 3, 4, 6, up to 6 dimensions. They're not too bad. They're not too, they're fairly convex. We don't have too much trouble there. And so but it takes time. So for us to run a compute for 6 rooftops, there's an additional level of detail that's in the paper about why this is difficult, because of there's some non-linearities in the solution. It takes us about 3-4 hours. But on the other hand, you're doing something which is going to last 15-20 years. So it should not be a problem.
There's also another question by Michela, Keshav.
Right. So the deterioration of PV panels with time. Yes. So the work we're doing is we're looking at the past history as giving us the net generation, and then extrapolating into the future. And then when you do the simulations, we are doing simulations based on these subsamples. Now, if you wanted to take degradation into the future, what we would need to do is to essentially incorporate into our simulations future time periods of time length t, like 100 days, which have degraded solar panels. Let's say it's a 5% degradation. So that would change the solar trace essentially. And so by changing the solar trace, we could accommodate that. So that would be the way to incorporate deterioration. But in fact, we have not done that, in part because there are no good models for PV deterioration that I'm aware of. I mean, if somebody knows about good models that keep up with the change in technology, I'd be happy to know, but at the moment, we haven't done that. I think Mohammed was asking about, is it Intel CPU? Yeah, it's 3-4 hours in a single Intel CPU. We did parallelize it. So we had access to a very large machine, which had 128 cores. So we were able to do a lot of parallelized things. But for a single optimization, with 3 to 4 hours in a single CPU, single core.
Mingguo Chen, do you want to ask a question?
Yes. Keshav, this is a very interesting work, and it's good to see there actually some analysis using the real world data as well. I just I'm not sure if I missed that, but or it has not been discussed. But I'm thinking in your final suggestion solution, there is some certain suggestion on the size of the solar panel to install, and as well as the storage.
Yes.
Yeah, I'm just curious. What if you enforce the solution to only output the suggestion, let's say using for only solar but no storage, and also at the same time, or on the other end, no solar at all, just a storage, and try to see is there any insight we can see by comparing your solution to these two extreme solutions in some sense? Maybe this can outline the benefit of considering both design space simultaneously.
Right. Thanks, Huang. That's an interesting suggestion. So, when you talk about solar only and no storage, right? Part of the work you're doing is basically the solar storage trade-off. So in the line, the Pareto frontier in case of the single dimensional case, or essentially it's a manifold in the multidimensional space. Those correspond to a certain amount of solar plus storage. So if we did solar alone, then we would have a reduced manifold, and we could try that. It didn't occur to us to do that. What would be the case? So, I mean, I think that's a great suggestion for future work. And then storage alone, I'm not sure what that means, because that's a single dimensional quantity, right? If you have only storage,
that's right.
all you're doing is storing from the grid and playing it back. That's trivial. I mean, so it's not research. It's a toy problem. So solar alone, I think is interesting. We could do it, I suppose. And I'm wondering. Yeah, there would be some intuition we could develop from doing that. Yes, but we haven't done it, and we could do that. Yeah.
Right. Maybe I'm asking this maybe because sometimes the storage system, people may concern it has some it could be of some danger. I mean, at home, so some people don't want to install it.
Yeah.
So it's just wondering. Yep. If people have that concern, how much would they lose in terms of the?
Sure. Yeah, no, absolutely. Yes. So, I mean, if we do solar alone, for the single dimensional case, single rooftop case, if we studied in the past, that again be trivial. But for the multi-rooftop case, I think again, it would be a reduced version of what we presented so far. And I think, I mean, all the analysis we've done, the Chebyshev bond, all those things will continue to hold. So I think it would be a very small difference to the work we've done. But we haven't done it, so we could certainly. I just took a note down to ask Brad to look into that, but that would be interesting to do. Thank you.
Right. I'm just curious about the comparison. Yeah.
Right. Yeah, it would be interesting. Yeah, it would be a reduced manifold, or one-dimensional reduction in the manifold dimensionality, but I think that should be okay.
Okay. Thank you, Keshav.
Okay, okay, no more questions. So thanks a lot. Thank you everyone for attending this session. So I'll hand it over back to the organizers, Ram, Antonella.
Yeah, if that's okay, I would just stop for now the recording. What do you think? Vijay, is okay? Okay.
Yes, yeah, it's okay.